My dear students, welcome back to our channel. In this video, I will be explaining the BSc 5th semester subject Chemistry, Spectroscopy and Chromatography as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 3, first important short question is: explain the principle of solvent extraction and describe the batch extraction method. Answer: solvent extraction is a separation technique used to transfer a substance from one liquid phase into another based on its solubility. Usually, one phase is water, aqueous, and the other is an organic solvent, like ether or chloroform, that does not mix with water. The substance to be separated moves into the solvent in which it is more soluble. Principle: it works on the principle of distribution or partition law, which states that a solute distributes itself between two immiscible liquids in a constant ratio at constant temperature. Batch extraction: in this method, the aqueous solution containing the solute is shaken with a fixed volume of organic solvent in a separating funnel. After shaking, the two layers separate and the solute-rich solvent layer is collected. Example: iron. 3 ions can be extracted from an aqueous solution using an organic solvent containing tributyl phosphate. Easy tip: like dissolves like the solute moves to the solvent it prefers. Next important short question is: to discuss Craig's counter-current extraction method. Answer: Craig's counter-current extraction method is an advanced form of solvent extraction used to separate components of a mixture more efficiently. It works on the principle of repeated distribution of solutes between two immiscible liquids, usually water and an organic solvent. In this method, a series of interconnected tubes or chambers are used. Each tube contains the two immiscible liquids. The solute is allowed to distribute between them according to its solubility. After equilibrium, one layer, usually the organic phase, is transferred to the next tube while the aqueous layer remains. This process is repeated many times, leading to a gradual and effective separation of the components. Example: Craig's apparatus is used to separate amino acids, drugs, and natural products based on their partition between the two phases. Easy tip: think of it like many extractions in a line. Each step purifies a little more until the components are neatly separated. Next important short question is: 3 write the principle and theory of thin layer chromatography. Answer: thin layer chromatography, TLC, is a simple and fast method used to separate and identify small amounts of compounds in a mixture. It works on the principle of adsorption. Different compounds are adsorbed, stuck on the surface of a solid, stationary phase to different extents and move at different speeds with the solvent, mobile phase. A thin layer of adsorbent like silica gel or alumina is coated on a glass or plastic plate. The sample is spotted near one end and placed in a jar containing a solvent. As the solvent rises by capillary action, it carries the sample components upward. Components that are weakly adsorbed move faster, while strongly adsorbed ones move slower, leading to separation. Example: TLC is used to check the purity of drugs or to monitor the progress of an organic reaction. Easy tip: the faster it moves, the weaker it sticks. That's the heart of TLC. Next important short question is: 4 explain the principle of paper chromatography. Answer: paper chromatography is a simple and inexpensive technique used to separate and identify colored substances like pigments or inks. It works on the principle of partition. The components of a mixture distribute themselves between two phases, the stationary phase, water molecules trapped in the paper fibers, and the mobile phase, a solvent that moves through the paper. When a drop of the mixture is placed on the paper and the paper is dipped in a solvent, the solvent moves up by capillary action. Different components travel at different speeds depending on their solubility in the solvent and their attraction to the water in the paper. This leads to clear separation of spots. Example: it is used to separate plant pigments like chlorophyll and carotenoids or to test ink dyes. Easy tip: think paper holds water, solvent runs fast, how much each loves them decides who comes last. Next important short question is: 5. Define retardation factor, RF, value and explain the factors affecting RF values. V.IMP. Answer: in chromatography, the retardation factor, RF value, helps to identify substances by showing how far each component travels on the chromatogram. It is defined as RF is equal to distance traveled by the substance, distance traveled by the solvent front. The RF value is always less than 1 because the solvent moves farther than any component. Example: if a dye spot moves 3 cm and the solvent front moves 6 cm, RF is equal to 3/6 is equal to 0.5. Factors affecting RF values. Nature of the compound: polar compounds move less, giving smaller RF values. Nature of stationary phase: more polar adsorbents, like silica gel, hold compounds more strongly. Solvent: mobile phase: a more polar solvent increases RF values. Temperature: higher temperature can slightly increase RF. Easy tip: remember, RF tells who runs faster. The less the attraction to the plate, the farther it goes. Next unit 3. Long questions. First important long question is: explain continuous extraction process. Answer: continuous extraction is a method used in solvent extraction to separate a solute from one liquid phase into another more efficiently and completely. It is especially useful when the solute has low distribution ratio, meaning only a small portion transfers in one extraction step. Instead of repeating several batch extractions, the process is made continuous, so the extraction occurs again and again automatically until the solute is completely transferred. Principle: the process works on the distribution or partition law, which states that a solute distributes itself between two immiscible liquids in a definite ratio depending on its solubility. In continuous extraction, fresh solvent keeps contacting the aqueous solution continuously, so equilibrium is constantly renewed, improving extraction efficiency. Process: in a continuous extractor, like a Soxhlet extractor, the aqueous solution is placed in the main chamber. The solvent is heated, its vapors condense and fall on the solution, dissolving the desired solute. The solute-rich solvent flows back into the boiling flask, leaving behind the impurities. This cycle continues automatically, ensuring maximum extraction without repeated manual steps. Example: continuous extraction is used for determining iron 3 ions using organic solvents like tributyl phosphate, TBP. Extraction of natural oils from seeds and leaves. Separation of metal ions in analytical chemistry. For instance, when extracting Fe superscript 3 ions, the aqueous solution of iron is continuously contacted with the organic solvent. The iron complex gradually moves into the solvent phase until no more remains in water. Advantages: complete extraction of solute. Saves time and solvent compared to multiple batch extractions. Useful for low concentration samples. Easy tip to remember: Think of continuous extraction like washing clothes in a running stream. The clean water, solvent, keeps flowing and removing dirt, solute, continuously until everything is clean, fully extracted. Next important long question is: 2. Describe the determination of iron. 3. By using solvent extraction. Answer: the determination of iron. 3. By solvent extraction is a common analytical method used to estimate the amount of Fe superscript 3 ions in a sample. It combines chemical reaction and solvent extraction principles to separate and measure iron easily and accurately. Principle: this method works on the distribution law, where iron 3 forms a colored complex with an organic reagent that is more soluble in an organic solvent than in water. The intensity of the color in the organic layer is then measured using a spectrophotometer, which is directly proportional to the amount of iron present. Procedure: 1. Preparation of solution. Take an aqueous solution containing Fe superscript 3 ions. 2. Complex formation. Add an organic reagent like thiocyanate, KSCN, or phenol trifluoroacetone, TTA. Iron 3 reacts to form a red-colored complex such as Fe, SCN. 3. Extraction. Shake the solution with an organic solvent like ethyl acetate or amyl alcohol in a separating funnel. The red complex moves into the organic solvent layer because it is more soluble there. 4. Separation. Allow the two layers to separate. The upper organic layer, colored, is collected carefully. 5. Measurement. Measure the absorbance, intensity of color, of the organic layer using a spectrophotometer at the suitable wavelength, around 480 nanometers. 6. Calculation. Compare the absorbance with a calibration curve made using standard iron solutions to find the concentration of Fe superscript 3 in the sample. Example: this method is used in water analysis, ores, and food samples to find trace amounts of iron. Advantages: high sensitivity and accuracy, simple and fast separation, interfering ions can be easily removed. Easy tip to remember: think iron loves red. When Fe superscript 3 meets thiocyanate, it turns bright red and moves into the organic layer. The darker the red, the more iron you have. Next important long question is: 3. Give the classification of chromatography with a neat flow chart. Answer: chromatography is a powerful separation technique used to separate and identify the components of a mixture. It is based on the principle of differential migration, where each component moves at a different speed because of its different attraction toward the stationary phase and mobile phase. The substance that moves faster has less attraction to the stationary phase, while the one that moves slower is more strongly held. Classification of chromatography. Chromatography can be classified in different ways, mainly based on the type of stationary phase and mobile phase used. 1. Based on physical state of phases. Tight stationary phase, mobile phase. Example: gas chromatography, GC, solid or liquid on solid support gas separation of volatile organic compounds. Liquid chromatography, LC, solid or liquid on solid support liquid, TLC, paper chromatography. 2. Based on separation principle. Type basis of separation. Example: adsorption chromatography, difference in adsorption on a solid, TLC, column chromatography. Partition chromatography, distribution between two liquids, paper chromatography. Ion exchange chromatography, exchange of ions between resin and solution, separation of amino acids. Gel filtration, size exclusion, separation by size or molecular weight, proteins and polymers separation. Flow chart. Chromatography. Based on phases, based on principle. gas chromatography liquid chrome, adsorption partition ion exchange gel filtration. Example: paper chromatography, partition type, is used to separate plant pigments, while TLC, adsorption type, helps check drug purity. Easy tip: remember, a pretty intelligent girl is equal to adsorption, partition, ion exchange, gel filtration, 4 main types of chromatography. Next important long question is: 4. Describe the preparation, development, and application of thin layer chromatography, TLC, in the separation of organic compounds. Answer: thin layer chromatography, TLC, is a simple, fast, and reliable technique to separate and identify small amounts of organic compounds in a mixture. It is widely used in laboratories to check purity, monitor reactions, and identify compounds. 1. Preparation of TLC plate. A thin layer of adsorbent like silica gel or alumina is spread evenly on a glass, plastic, or aluminum plate. The plate is dried to remove moisture. Some plates come pre-coated and are ready to use. A small spot of the sample is applied near the bottom edge using a capillary tube. 2. Development of the chromatogram. The plate is placed in a chamber containing a small amount of solvent, mobile phase. The solvent rises up by capillary action, carrying the compounds along. Different compounds move at different speeds depending on their adsorption to the stationary phase and solubility in the solvent. After the solvent front reaches near the top, the plate is removed and dried. Detection of spots. Some compounds are colored and visible directly. For colorless compounds, visualizing agents like iodine, ninhydrin, or UV light are used. RF value. RF is equal to distance traveled by compound, distance traveled by solvent. Used for identification of compounds. 3. Applications of TLC. Checking purity of organic compounds. Monitoring progress of reactions in organic synthesis. Separation of plant pigments like chlorophyll, carotene, and xanthophyll. Identification of drugs and dyes. Easy tip to remember. Think of TLC as a race on a sticky hill. Compounds that stick less to the stationary phase run faster, travel farther, while those that stick more move slowly. The RF value tells how far each runner went, helping to identify it. TLC is popular because it is quick, sensitive, requires small sample, and gives clear results, perfect for any chemistry lab. Next important long question is: 5. Explain different methods of development of paper chromatography. Answer: paper chromatography is a method used to separate and identify mixtures like plant pigments, dyes, and amino acids. The separation depends on partition between the stationary phase, water in paper, and mobile phase, solvent. Once the sample is spotted, the chromatogram is developed using different methods. Methods of development of paper chromatography. 1. Ascending chromatography. The paper is suspended vertically in a chamber with solvent at the bottom. The solvent rises up by capillary action, carrying the sample components. Components separate based on their solubility and adsorption. Example: separation of amino acids using N-butanol, acetic acid, water. 2. Descending chromatography. The paper is arranged so the solvent flows downward due to gravity. Useful for long chromatograms or when solvent rises too slowly. Example: separation of plant pigments like chlorophyll. 3. Radial, circular chromatography. The sample is spotted at the center of circular paper. Solvent spreads outwards in all directions, forming concentric rings. Good for quick analysis of small samples. Example: separation of ink dyes. 4. Two-dimensional chromatography. Paper is developed in one direction using one solvent, then rotated 90 degrees and developed in a different solvent. Gives better resolution, separates compounds that overlap in 1D chromatography. Example, separation of complex mixtures of amino acids or sugars. Detection of spots. Colored compounds are directly visible. Colorless compounds are visualized using ninhydrin, iodine vapors, or UV light. Applications. Separation of plant pigments. Identification of amino acids and sugars. Checking purity of drugs and dyes. Easy tip to remember. Think of paper chromatography as a race track for molecules. Ascending, runners go up. Descending, runners go down. Radial, runners move outward in a circle. Two-dimensional, runners race in two directions to avoid crowding. This makes it easy to separate and identify mixtures clearly and effectively in any lab.